Looking at section 7.2, systems of linear equations in three variables, we are going to verify the solution of a system of linear equations in three variables, solve systems of linear equations in three variables, and solve problems using systems in three variables. So for instance, it says a system of linear equations in three variables and their solutions. In general, any equation in the form ax plus by plus cz is equal to d, where a, b, c, and d are real numbers, such that a, b, and c are not all 0, is a linear equation in three variables x, y, and z. A solution of a system of linear equations in three variables is an ordered triple. So now we're going to look at having an x, y, z in terms of that ordered pair. X, y would be a pair, x, y, z would be our ordered triple. So we have our ordered triple of real numbers that satisfies all equations of the system. The solution set of the system is the set of all of its solutions. So let's try an example. Determining whether an ordered triple satisfies the system. So show that the ordered triple, -1, -4, and 5, is a solution of the system. So all we're going to do is we're going to take and plug in -1 for x, -4 for y, and 5 for z, and make sure that it's equal, it's equivalent. So I have the three equations written down here on the bottom, and we're just going to plug in our values. So x value of -1 minus 2 times y value of -4 plus 3 times z value of 5. That would have to equal 22. So we'd have a -1 plus 8 plus 15. Is that equal to 22? -1 plus 8 is 7. 7 plus 15 is 22. So 22 is equal to 22. We're good with that one. If we were to try the next equation, 2 times an x value of -1 minus 3 times the y value of -4 minus our z value of 5, that would have to equal 5 to be a solution. So we'd have a -2, a +12, minus 5, that would have to equal 5. -2 plus 12, 10, take away 5, 5 is equal to 5. That works. And then we try our last one. So 3 times our x value of -1 plus our y value of -4 minus 5 times our z value of 5, that would have to equal a -32. So a -3 minus 4 minus 25. Is that equal to -32? -3 minus 4 is a -7. -7 take away 25. That would land us at a -32. So that is a solution. So our ordered triple is a solution of that system. So if we have to go about solving our system of linear equations in three variables, you would have done this in Algebra 2. Step number 1 says to reduce the system to two equations and two variables. Once you get it to two equations and two variables, then it's just like what we did yesterday. It says this is usually accomplished by taking two different pairs of equations and using the addition method to eliminate the same variable from both pairs. Step number 2, we're going to solve the resulting system of two equations in two variables, using addition or substitution. So depending on the type of equations you're left with, determine which is the easiest way to solve the regular system. It says the result is an equation in one variable that gives the value of that variable. We're going to, step 3, do some back substitute the value of the variable found in step 2 into either of the equations in two variables to find the value of the second variable. And that's going to give us 2 of our 3 answers. So for step 4, use the values of the two variables from steps 2 and 3 to find the value of the third variable by back substituting into one of the original equations. And then, as always, check the proposed solution in each of the original equations. You want to make sure all that work you do, you get the right answer. So let's try one. We have our 3 equations. X plus 4y minus z is equal to 20. 3x plus 2y plus z is equal to 8, and 2x minus 3y plus 2z is equal to -16. So step number 1, they want us to reduce the system of two equations into two variables. So basically what you're doing is you're going to look at the x values and decide, is it easy to eliminate x? Is it easy to eliminate y? Or is it the easiest to eliminate z? So when I look at these, I think the easiest way is going to be to eliminate the z's. And why is that? Because I see I have a plus z and a minus z, and I know if I add those two equations, I'll be able to cancel out z easily. And then this last equation has a 2z, and I can easily turn one of those into a 2z by multiplying by 2. Now, which one would I use? I would end up using that top one because I already have a positive down here in the third equation, so I would aim for that negative in that first equation. So let's take this one step at a time. We're going to start by taking care of those first two equations. If I were to group these first two equations together, this is going to give me my first new equation. And all I'm going to do is I'm going to just rewrite these. X plus 4y minus z is equal to 20. And 3x plus 2y plus z is equal to 8. And I can go ahead and I can cancel out my z's by adding those two equations together, because a negative z and a positive z, when I combine them or add them, cancels them out. So if I add those two equations, that's going to leave us with x plus 3x gives us 4x plus 6y is equal to 28. Now, that's all I'm going to do for right now. That's my first equation. Now, I need to use this third equation here with one of those other two. And so what I'm going to do is I'm going to pick this first equation and that last equation for the means that I mentioned, and this is going to give me new equation number 2, I guess I can call it. And in order to make a positive 2z and a minus z cancel each other out, I need to multiply that first equation by 2. So if I take that first equation, I multiply by 2. This is going to give me my new second equation. If I go ahead and distribute that 2 out to everything, that's going to give us a 2x plus an 8y minus 2z is going to equal 40. And then I'm just going to rewrite that third equation just as is. So we have a 2x, a minus 3y, a plus 2z is equal to negative 16. And now when I take these two equations, I'm going to cancel out my z's, again by using addition, because a negative 2z and a positive 2z naturally cancel, so we use addition, we combine. So 2x plus 2x is a 4x, 8y added with negative 3y is a 5y, and that's going to equal 40 added with a negative 16 would leave us with 24. And now I have two equations here that have two variables, and we're back to what we just did. So step number 2. Step number 2 says to resolve the resulting equation of two equations in two variables. So I'm going to take those two equations and I'm going to stack them. We have a 4x plus a 6y is equal to 28. We have a 4x plus a 5y is equal to 24. And just like what we did in section 7.1, our goal is to eliminate one of those variables now. Well, when I look at those two equations, I notice that I have a 4x and a 4x. And if I subtract the two equations, it's going to give me 0x, which is going to cancel out the x. So that means I'm going to take and I'm going to subtract my second equation from my first equation. So if I have a 4x take away 4x, I cancel out my x's. I have a 6y, then I'm going to take away 5y, which leaves me with 1y. And I have a 28, I'm going to take away 24, that's going to leave me with 4. So far we found that x, do we have a value for x yet? No, we don't have a value for x yet. So far we have a y value of 4, and we don't know what z is equal to yet. So once I know that y is equal to 4, that was my step 2, we could go ahead and figure out what y is equal to, or sorry, what x is equal to. So that's going to be in step 3. Step number 3 says to use back substitution in one of the equations in two variables to find the value of the second variable. So I need to pick one of these two equations over here to plug in my y is equal to 4 to solve for what x is equal to. It really doesn't matter which one you pick. I might just pick the top one. 4x plus 6y equals 28. So if we have 4x plus 6y is equal to 28, and we just said that y was equal to 4, let's see what we got. 4x plus 6 times 4 equals 28, which means 4x plus 24 is equal to 28, which means 4x is equal to, if I subtract that 24 over, I get 4. That means x is equal to 1. So now we know that x is equal to 1. We know that y was equal to 4. Z is still our unknown. So that's where we go to step number 4. Step number 4 tells us to back substitute the values found for two variables into one of the original equations to find the value of the third variable. And then in step 5, we're going to check it. So I'm going to pick one of these original equations. I might pick this first equation. So if we have x plus 4y minus z is equal to 20, we said that x was equal to 1 and y is equal to 4, we can figure out what z is to equal 20. So let's see, we have 1 plus 16, so we have 17. Take away z is equal to 20. So if I were to solve to get z all by itself, I'd subtract 17, so negative z would equal 3. If I divide by negative 1, z is going to equal a negative 3. So I found my x, y, z ordered triple is going to be a 1, a 4, and a negative 3. Now I know that that worked in my first equation because I just used that to solve in step 4. It doesn't hurt to do a quick check with some of these other ones. So if I were to take a 3 times 1 and add 2 times 4, and then add a negative 3, is that equal to 8? So we'd have a 3 plus 8, which gives us 11, added with a negative 3 is equal to positive 8. So that works in the second equation. And a quick check in the third equation. We'd have 2 times 1 minus 3 times 4 plus 2 times negative 3. That has to equal negative 16. So 2, take away 12, take away 6, negative 16. 2 minus 12 is a negative 10. Negative 10 minus 6, negative 16. That also works. We are good with our ordered triple of 1, 4, negative 3.